Next, we are going to look at a new cipher. So if we think of allowing P to be a large prime number, and we pick our key space, our plaintext space, and our ciphertext space all to be the multiplicative group FP, or multiplicative field, I should say. Then what we're going to think about is a function EK, so the encryption given this K, whatever we pick, to be congruent to K times M mod P. So again, we're taking the message as a number and multiplying it by K, and then mod P, okay? And then what would the decryption function be? Well, then if we want to undo the multiplication, right, we need to do the opposite of multiplication, which we normally think of division, but in a field, a finite field of P elements, remember we would do the inverse of K. And then just so you know that the textbook uses K, so they define K inverse as K prime. Okay, I don't know why, they just do. Okay, so as you're reading the table and you come across that, just be aware. Okay, so then we want to next think about, is this a successful crypto system? Okay, so is it easy to encode? Yep. Computers can do this sort of thing really fast. Is it easy to decode given the key and given all the other information? Yeah. Okay. Now imagine that it were intercepted. Okay. Is it hard or is it easy to figure out if the message is it easier or difficult to determine the plain text? Well, that kind of depends. Maybe. So by hand, yeah, it's hard. Okay, because again, P is something very large. We're talking between 2 to the 150 and 2 to the 160, something like that. But for a computer nowadays, well, not so much. Okay. Again, it might take some time, but it will be vulnerable. Okay, and then certainly, the more information we have for number 4, a computer can piece that together really quickly. So I would say, yeah, 4 is not going to work in our favor. So again, that's the idea that if we have a string of things that we say, okay, well, this ciphertext matches this plaintext, and we have that a few times, this is going to fall victim to interception quickly. So maybe what we could do is extend this idea of multiplication just a bit. And so the Affine Cipher does just that. This does generalize into the Hill Cipher, which we will see in group work. But the idea here is you pick 2 keys, okay, K1 and K2. Again, that the space hasn't changed at all. And what we define encryption and decryption as is that we take the message and multiply by K1 and add K2. Okay, and then we do the whole thing mod P. Okay, so there's a little bit of a Caesar shift in here too. And then similarly, we would decrypt by doing K inverse, and if you think about just undoing order of operations here, we would take the ciphertext, that should actually be C, and we would do C minus K2 first, and then do K1 inverse, and then mod P, of course. Alright, and so then that would get us back to the plain text. Okay, so then we just need to check, okay, these, if we do compose them, they do end up being inverses. So existence of inverses implies that the functions are one-to-one and onto, but why is it surjective, why is it onto, and why is it injective? And so that surjective is just, do we map everything onto the set of all possible ciphertexts? Yeah. Because again, since our key text, our key space, our ciphertext space, and plaintext space is all FP, yeah, it's going to be onto. and we're doing arithmetic within that, so it's a field, it's closed, all that good stuff. And injective, is it one-to-one? So if you take 2, so if you end up, saying at the end of the day you get 2, and then you have another message that gets 2, well, if we know that those are equal, does that imply that so these are the C's, C1 and C2, does that imply that our messages are the same? And it is going to be the case, since there's a defined process here, this is going to work. So it is going to be both injective and surjective. Good thing to do as you create encryption systems. And then is it successful? Well, encryption, decryption, still relatively easy because we have a known method. We can put it in a computer and it'll do it lickety-split. In terms of interception, if a message gets intercepted, how easy is it to break it? Well, it's better than the multiplicative stuff that we saw above, but still it's going to be a little vulnerable. So this is okay, at least given modern day standards. Okay, so we'd still like to do something better, but it's still an interesting cipher. And we talk about this as a symmetric cipher, and why is that symmetric? So the idea of symmetry here is that if the same information is available to both Alice and Bob, maybe not Eve necessarily, but Alice and Bob would have the same thing. So we have the keys are known, and then the encryption and decryption method is known to both. So they have the same information. And if that information, or if that possession of information would shift, so say Alice had a bit more information than Bob, then we would call that asymmetric, and we will see that later on. But so just an overview of the Affine cipher, and then in class we'll see how the Hill cipher works as well.